Here we have a second order linear constant coefficient homogeneous differential equation. So second order linear constant coefficient and homogeneous because we have a zero over here. Let's assume the independent variable is t. Our dependent variable, of course, is y. So what we're going to do is try to find a solution to this equation. Now, you can see that what we're doing is taking a function, multiplying by 3, and then take the derivative of that function and the second derivative of the function, and we're combining all those things, the function, its first derivative, and second derivative, somehow to get 0. And so the only way that could happen is if the function and its derivatives were all very similar to each other. And the one place that happens is when we have exponential functions, because the derivatives of exponential functions are essentially the original exponential function. So let's assume, as a guess, that y looks like e to the rt, where r is some constant. Now, if we do, then the first derivative y prime is r e to the rt, and the second derivative is, by the chain rule, we have another r out there, so r squared e to the rt. So let's substitute these things into the differential equation, and because we're trying to force this to be a solution, we'll actually set it equal to 0. So when we substitute those things, we have r squared e to the rt minus 2 r e to the rt. So remember, r squared e to the rt is the second derivative. R e to the rt is the first derivative, but we have to multiply by negative 2. Minus 3 times our original y, which is e to the rt, equals 0. Okay? So what we find here is that each term has an e to the rt in it, so we can factor that out. We get e to the rt times r squared minus 2r minus 3 equals 0. Now this is a multiplication, so we have a product of two things, these two things, and the product is 0. E to the rt, or e to the u, is greater than 0, regardless of what u is. Okay, so for all u. So that means this is greater than 0, so it can't be equal to 0. So that means this remaining part must be equal to 0. So let's set it equal to 0, and at the same time let's solve. We get r minus 3. We're solving by factoring. R minus 3 times r plus 1 equals 0. So I'm setting this part equal to 0 and factoring. And so now I have a product of two things that equals 0. So that means one or the other has to be 0, which would occur when r was 3, or r equals negative 1. Okay, so as solutions then, that gives us two possible solutions. Remember, our assumption was that y equals e to the rt, and so we have y equals e to the negative t, and y equals e to the 3t are both solutions, or should be solutions, to our original differential equation. And you might remember what we saw earlier is that if we multiply either of these by a constant, any constant, it will still be a solution. And in fact, I'm going to claim that if we multiply each by some constant and we add them together, that this, in fact, is a solution to the differential equation. So let's check and see if that's true. Let me take this guy. I'm going to move it up here. Well, I'm going to take its derivative and put the derivative up here. So if I do that, the derivative of this is y prime equals negative c1 e to the minus t plus 3c2 e to the 3t. And the second derivative is y double prime again we'll multiply by a negative, so that turns this back to positive, is c1 e to the minus t. And here we have to multiply by 3 again, so plus 9 c2 e to the 3t. And what we want to do is see if this function here is a solution to our original ODE. So let me put these guys into the left-hand side and see if we in fact get 0. So the left-hand side equals the second derivative, so that's going to be c1 e to the minus t plus 9 e to the 3t minus 2 times y prime, so that's negative c1 e to the minus t plus 3 c2 e to the 3t. And let me move the paper over, give us a little bit of room here to work with. So, and then we have to subtract 3 minus 3 times our y, which is c1 e to the minus t plus c2 e to the 3t. So if we then distribute, we can get rid of these two guys. So we have c1 e to the minus t plus 9 e to the 3t. And then here we have plus 2 c1 e to the minus t and minus 6 c2 e to the 3t. And then minus 3 c1 e to the minus t and minus 3 c2 e to the 3t. And so let's combine like terms. Let's see, let's look for the e to the minus t's. We have a c1 e to the minus t. There's 2c1 e to the minus t, so that's 3c1 e to the minus t. And there's a minus 3c1 e to the minus t. So those three cancel. And then here you can see we have, I lost my constant here, that was a 9c2. So there should be a c2 in here, which means a c2 in here. And so we have 9c2 e to the 3t minus 6c2 3 to the t minus 3. So 9 minus 6 minus 3 is in fact 0. Okay, so what that shows us is that this thing in the box is in fact a solution to our equation, because when we put it into the left-hand side, simplified, the result was 0, the right-hand side. So this is what always happens when we have a second-order linear constant coefficient homogeneous equation, and when we get when we substitute y equals e to the RT, if we get two values of r that are real numbers and they're distinct from each other, then our solution always looks like this. Okay, so let's summarize what's going to happen in general. The other two cases that come up, I'm not going to show you why they work the way they do. That is done in some other videos. But for now, let's just look at what happens for the three cases that can occur. So when we're solving a y double prime plus by prime plus cy equals 0, okay, where a, b, and c are constants, when we solve that, what we get is we basically will make the same kind of substitution as we did before. We'll let y equals e to the RT. And we always come up with an equation like this that needs to be solved. And if you look at this carefully, the coefficients of r, this is just a quadratic equation. The coefficients of r are the coefficients from our original differential equation. So I'm going to call this thing usually the auxiliary equation. Some authors will call it the characteristic equation. So when we're solving this thing, we have the auxiliary equation, AR squared plus BR plus C equals 0. And the solutions we oftentimes call roots. Okay, not to be confused with square roots. So I'm going to use that language, the roots of the auxiliary equation, or the characteristic equation as some people call it. So there's three things that can happen. The first thing is that we have two real roots, or solutions, to the auxiliary equation. And let me say I call those roots R1 and R2. Okay, in that case, then the solution to our ODE, to our homogeneous ODE like this, is the solution is y equals C1 e to the R1t plus C2 e to the R2t, which is exactly what we saw in our previous equations, example. So see, we have two arbitrary constants because we're solving a second order differential equation. The second thing that can happen is if when we factor, both factors come out the same, then what we have is one real root. So if we have one real root, R, then what the solution looks like in that case, the solution has to have two parts, and yet we only have an e to the RT. So the solution, it turns out, looks like C1 e to the RT plus C2 t e to the RT. Now the reason for that, again, is explained in another video, and I'll go through that in class very likely. But we have these two factors of e that look the same, but we have an extra factor of t on this one. And then the other thing that can happen is we can get two complex number roots, so two complex roots. Now how would we find such roots? Well, we'd find them by solving the characteristic equation using the quadratic formula, and when we did, we'd end up with square roots of negatives, which would give us i's. So if we have our two complex roots, which I'm going to call them k plus lambda I and k minus lambda I. Okay, so these are complex numbers. They have a real part, they have a complex part. And notice if we have two complex roots, they're going to be what we call complex conjugates of each other. And in that case, the solution will look like y equals, there's going to be an e to the kt, that's from these parts, and then times the quantity C1 sine of lambda t plus C2 cosine of lambda t. And that also is shown in another video, and we'll do that in class as well. So the reason for this, we're not going to go over right here, but what we want to recognize or remember is that when solving a homogeneous equation like this, second order linear constant coefficient, that we have to solve the auxiliary equation. When we do, we can get either two real roots, which means we have a solution that's a sum of two exponential functions. We can get one real root. The solution then is the sum of an exponential function and t times that exponential function. And if we have two complex roots, then our solution is the product of an exponential function and a combination of a sine and a cosine. So that wraps that up. The next video will run through, remember when we're solving something that looks like this, ay double prime plus by prime plus cy equals f of t, that we decided that the solution looked like y equals y sub h, the homogeneous solution, which is what we've gone over finding here, plus y sub p, the particular solution. So in the next video, we'll look at how to find this y sub p, the particular solution.